Okay, good morning. So let us start today's lesson. So what I want you to concentrate on is in the middle projector. So I will scroll up and down and show you things. But then when I want to write on iPad, I have to switch. Then you can see there if you want to see the PDF file still, okay? I hope that I can manage all of these things when I'm teaching, but hopefully I will be able to do that, okay? Okay, so now let us actually go and so do you remember we talked about the inverse of a matrix and we discussed the content of this theorem, and the last one we learned was this actually, that if you have A and B invertible matrices, if you multiply them it will become a new invertible matrix. And then if you want to determine the inverse of the product, you can individually make the inverse, but what you need to be careful is that you have to reverse the order of multiplication. Yes? So this we learned last time, and we also proved the theorem. Okay, so here we have this consequence of this theorem. This is also something we discussed last time. If I have the negative of a matrix, if the matrix, of course, is invertible, its negative is also invertible, and it is equal to the negative of the inverse matrix. Okay, and then I don't remember exactly, did we discuss about this property or not? Do you remember? Okay, so let us just try. Yeah, okay, so let us just try to review a little bit here. So we want to see that this is also very important to know. If I have a matrix A, if I raise it to power n, if my matrix is invertible, if I raise it to power n, then I want to take the inverse. I can commute these operations. I can first make the inverse to get a new matrix and then raise it to power n. Yes, this is what we actually have. So let us try to review this. Why do you think this formula is correct? So let me go back and then try to write you something here. So we had this formula, if you remember, that A times B, if A and B are invertible, then AB to the power of -1 is equal to the inverse of B first multiplied by the inverse of A. Now, what happens, for example, if I choose A and B the same matrices? Then instead of A, I just write A. Instead of B, I again write A. So what will happen? This becomes A times A to the power of -1. So wherever I see B, I am allowed to put A if they are equal. So then what happens? This becomes A inverse times A inverse. But if I ask you what is A times A times A is A squared, and I have the inverse of that, so this becomes A squared inverse. And if I ask you what can I write for the right hand side, it will tell me that I have a matrix A inverse which is multiplied by itself. So this means that this is that matrix to power 2. Okay, of course this is not the general proof, but hopefully you understand the idea is more or less the same. So it doesn't matter if I raise to power 2 and then take the inverse, or if I take the inverse first and then raise it to power 2, the results are the same, even though it is not trivial at all. Okay, and of course, if you know mathematical induction, which hopefully you know from Math 5, you can actually use mathematical induction to prove the general story. Yes, I want you to know these formulas. Okay, so now let us actually go back here. We want to solve this example. Let A and B be invertible matrices. Simplify this expression as much as possible. Okay, I want to pause recording, wait for you to do it yourself first. This is a simple exercise, but I designed this one a little bit hard. Okay, so if you think that is too easy for you, don't waste your time. I recommend you do it quickly and then go to this one. Okay, and then we come back together and solve the problem. Okay, I pause recording now. Okay, so this one is simple. So let me ask your opinion. Did you get this question mark here? Of course, if this is simple algebra, this is extremely simple problem. Even Math 1C students can solve that problem if A and B are numbers. But here, A and B are matrices, invertible matrices, and then we want to simplify this as much as we can. So this problem is designed so that you can, by practicing, you can memorize the rules applying for matrices. Okay, so did you get the answer to this question mark? No? Okay, so let me try to do it. Okay, so how should I do that? You can help me to do it. So here I see that I have an inverse here, and then I have the product of two matrices. The same here. I have the product of two matrices and I have the inverse. So what is the general rule here? If x and y are matrices, they are multiplied, if of course they are invertible. And if I want to find the inverse, I can find the inverse of y first, find the inverse of x, and then multiply the inverse of y from left to the inverse of x. So I will do the same thing. So this becomes the inverse of the second matrix, but here the second matrix is b squared. So this becomes the inverse of my second matrix multiplied by the inverse of the first matrix. So what I have written so far is the expansion of this expression. And I will do the same thing here. So what happens, it becomes A inverse, the inverse of my second matrix multiplied by the inverse of my first matrix. If you have any questions, please let me know. Okay, so let us continue. What can I do, for example? There are two things that hopefully you remember. What is A inverse inverse? It is A. B inverse inverse is also B. Okay, so let me just continue. So this becomes B2 inverse, and this becomes A times A inverse, and then I have B. Okay, so but you know what is the answer to the middle one? What is the answer to the middle one? Is the identity matrix. So when I multiply the identity matrix, I can just simply ignore that, and then what is left for me is b to the power of 2 to the power of minus 1 times b. Can I simplify this more? So how should I do that? Yeah, we just learned that we can interchange the role of power and the inverse. So I can write it as b inverse and then to power 2 and then multiplied by b. But what is the meaning of b inverse to power 2? b inverse to power 2 means multiplying b inverse by itself 2 times, yes? So instead of b inverse to power 2, I wrote b inverse, but this one is now what? Identity matrix. So this becomes b inverse times the identity matrix, and the answer finally becomes b inverse. So the answer to the question mark is just b inverse. So this is a very simple exercise, but you need to know how to do this algebra in matrices. Is that clear? Okay, but the second question is actually a little bit hard. Okay, so if I go to that question, so you can see there, so it is, let me also switch to here. So here A, B, and A plus B, and A minus B are all invertible matrices. Be careful. If A and B are invertible, there is no guarantee that A plus B and A minus B are invertible. So this is why if I want to use the inverse of these matrices, I have to explicitly mention that A plus B and A minus B are also invertible. But if A and B are invertible, we saw that the product is always invertible. But that is not true for the addition or subtraction of two matrices. So if I want to use them, I have to implicitly mention that all of them are invertible matrices. So we want to prove that this is equal to that. And this problem I consider it a little bit hard because there is no formula for A minus B inverse. Yes, we had the formula for AB inverse. It was B inverse times A inverse. But there is no particular formula for A minus B inverse or A plus B inverse. Okay, so that is a little bit harder than the previous problem. So do you have any suggestions? I don't want to do it. I just give you a hint if you don't know how to start. Because it seems that we don't know, we even don't know how to budge here, yes? Because A minus B inverse is A minus B inverse. We cannot write something for it. And the same thing for A plus B inverse. This thing that I want to tell you, I want you to have it in the back of your head somehow. In matrix theory, this is useful. Okay, let me write something and then you tell me why this is true, and then you can continue yourself, okay? So what I want to do, because this is an identity, I want to prove the left-hand side is equal to the right-hand side. So let me write like this. I would say the left-hand side is equal to, you tell me why this is true. I open a little bit bigger pair of brackets here, okay? And then I put A plus B first, and then I put A minus, and then I put A minus B, and then I put an inverse. Do you believe what I have done is correct? I am claiming that I want to start from the left-hand side and reach to the right-hand side. I am claiming that what you see here on the left-hand side can also be rewritten in this form. Is that understandable why?
Since they're all individually
Invertible.
you can include this.
Okay, but how? Elaborate a little bit more.
I can't elaborate further.
So, for example, let me do the other way around. By the way, when you read math texts, you shouldn't get puzzled. You should be working. You should study actively. Okay, why this is equal to the left-hand side? Okay, so assume that I have given you this from the beginning, and you want to expand that. Can you expand this? Because that is now a product.
Yes.
And then you want to inverse the product. So how do you do that? You start inversing them individually, but from the right-hand side to the left-hand side. You have to reverse the order. It's like the transpose. So if I ask you to open this up, you start taking the last one inverse first. You take the middle one inverse second, and you take the first one inverse last. Do you agree? So if I ask you to open this up, this is possible.
Mm-hmm.
And then what is the middle one now? A inverse
A.
Is A. So you get exactly the left-hand side.
Yeah.
Is that clear? I mean, if you don't have experience in these kinds of calculations, you might say, okay, why this is good? But if you have some experience, that is the goal of this example. I want to transfer this experience to you as well. But at least you understand that this expression that I have written here and this expression that I have here are exactly the same. Do you agree with that one or not? Yes? Okay. I want now to pause recording a little bit to see that how this will help you to continue and reach to the right-hand side. I want you to fill up these gaps. So I want to give you a little bit of time to think. So let me just tell you here, you see that I couldn't continue at all because there is no formula here, there is no formula here. Okay, let me ask your opinion. If I had written something like this from the beginning, what is the first thing you think about? If you want to do something with this expression, what do you do? So it's minus 10. Is your brain frozen?
Yes.
Yes. Okay, so a minus b times a plus b. If you wanted to do something with this kind of expression, what do you do? What is the natural step to do first? Just say something. You're just multiplying them, yes? Yeah, multiply, expanding. And that's the same story here. And that was the reason behind this trick. Because I couldn't even distribute anything here because I need to do this one first, which I don't have any formula to it. So I use this trick to get rid of minus sign here, minus 1 here, and transfer the minus ones to the middle one, which is now a single matrix. So what you can do, you can start expanding this expression. At least it is better than doing nothing, yes? So you just expand that, which is very simple, and use the same trick for the right-hand side and expand that and compare the expanded versions. If the expanded versions are the same, so it means that they are also the same. Yes, is that clear? Okay, just do it. Everything on this part today. Okay, so how we continue? I don't know. For example, I decide to keep it like this, and I start distributing this inside, yes? So that's possible. So what we do, I put this pair of brackets, yes, and I have still a minus 1 up there. I keep a plus b as it is, but I multiply a inverse inside. Okay, when I multiply a inverse by a, what do I get? I get I, and when I multiply a inverse by minus b, there is nothing much I can do. I can just simply write a minus 1b. Yes? Understandable?
Yes.
And then I expand once more. I can distribute once more. So again, I put my pair of brackets with minus 1 on top, and then I start multiplying a here and there, and I multiply b here and there. Okay, so a times I is a, but what is this one? If I multiply a by a inverse b, can you immediately see what is the result? B, because a multiplied by a inverse becomes I multiplied by b is just simply b, and the sign is negative. And then I take b and multiply it inside, so b times I becomes b. But tell me, can I write b a inverse b as a inverse b squared or something like that? No, because there is no guarantee that I can interchange them. Matrices or the matrix multiplication is not commutative. So I have to write minus b a inverse b. But of course, I can simplify one more step because minus b and b are cancelled. And what is left for me is a minus b a inverse b, and then totally inverse. Yes? Okay. But I cannot continue any further because there is no formula for the inverse of the difference of two matrices. So I have to stop there. But I can use the same trick for the right-hand side and see hopefully that at the end I will get up the same expressions. So I will start from the right-hand side, and I will do this a little bit quicker because we know what the rule is. So I rewrite it in this form. I write a minus b first, and then I write a inverse, and then I write a plus b. Yes, if you don't understand, please ask me questions, but that's very simple. So then I decide to keep a minus b as it is, and I multiply a inverse inside. A inverse a is just I, and then I have plus a inverse b, and then I have a total inverse on top. I distribute once more. So this becomes a times I, which is a times a minus 1b, which is b, and then minus b times I, which is minus b, and then minus b times that one is minus b a inverse b. Yes, so let me write them. So this is just a plus b minus b, and then minus b a inverse b, and then I have a minus 1 on top here. And then you see that again, this minus b and b are cancelled. So what do I get at the end is a minus b a inverse b inverse. So if I give this number 1, yes, and I give this number 2, I hope that you agree that by comparing number 1 and 2, the left-hand side is equal to this expression, which is exactly this expression. So this means that the left-hand side and the right-hand side should also be equal. So from comparing 1 and 2, I can conclude that the left-hand side is equal to the right-hand side. And that is the end of this problem. Yes? Any questions here? And this was a tricky problem, but if you know the rules, so you have some more tool in your toolbox in solving problems here. Any questions? Okay, so now the next step will be actually talking about negative integer powers of a square matrix. We haven't done that before. Yes, so far I gave you a matrix A. I could ask you to calculate a squared, or I can ask you to calculate a to the power of 3, a to the power of 4. Yes, positive integers. But now that we have the inverse, we can also talk about negative integer powers. Yes. So what is your opinion about how should we define a to the power of minus 2, for example? First of all, do you think a to the power minus 2 always exists? We want to define, but I want you to define it as if you are the mathematician. So how do you define a to the power minus 2? How do you define a to the power minus 3? How do you define that?
The inverse to that power. Like
yeah, exactly. So when you say a to the power minus 2, it's a good idea to follow the same rule for numbers. If I go back here, so if I ask you, if a is a number, which is of course not equal to 0, yes, and then what will happen if I ask you what is a to the power minus 2? You know what is the meaning of a to the power minus 2. Of course, in algebra, you write a to the power of positive 2, but we do not have division in matrices. This is another way to say that a to the power of minus 1 to the power of 2. Yes? So if I ask you what is a minus 3, a to the power of minus 3, another way of saying that it is a minus 1 to the power of 3. Yes? Okay, so that's the same idea. We want to follow the same rule for matrices. So if A is an invertible matrix, and N is a natural number, if you tell me a to power minus n, it means a to power minus 1 to the power of n. Yes? So this is by definition. And then do you remember we had another formula? If someone tells you no, I want to define it in that way, do you agree with him or her?
Yes.
But that's also true because we just proved that these two are equal. If they exist, they are equal. So by the way, I prefer to define it like this, but if someone tells like that, it is not a good idea to define it like this, but it is good to know that these two are the same, so it doesn't matter. So that's the definition. What Aaron said, I would agree with that one as well, okay? So now we go here, and then we have a lot of properties about negative powers. Okay, so now I want you to know that all the rules that we learned for positive powers can also be applied for negative integer powers. Yes. Okay, so these rules are exactly the same, but of course you have to sit down and convince yourself that this is, again, it is true. For example, I don't know, if we want to, for example, let me just try to give an example of this. Okay, so here, if I ask you, why do you think this is true? Why do you think a to power minus 2 times a to power minus 3 is a to power minus 5? Yes, but why this is true? So I just want you to see that the same rules with positive powers still apply for negative powers, but the definitions are different. By itself, there is no guarantee that this should be the case, but this is the case. Why is that? We want to prove that a to power minus 2 times a to power minus 3 is really a to the power of minus 5. So how should I do that? Yes?
You can rewrite them as a to the minus 1 to the
2, exactly. So what I want you to come with me until the end. So I will start from the left hand side. Instead of a to the power of minus 2, I used my definition, which is a to power minus 1 to power 2. And a to the power of minus 3 means a inverse to the power of 3. Okay, how can I continue further?
You can write a to the minus 1 times a to the minus 1. And then you'll have 5 in total.
Or, yes, that's correct, but you can use the rule for positive powers. For the positive powers, we learn that we can add the exponents.
Yeah.
So we do the same thing, because the bases are the same. So I have a matrix to power 2, the same matrix to power 3, but now 2 and 2 are positive. We learn that for positive powers, this rule is applied. Yes? So what I can do, I can write a minus 1 to the power of 5. But if I ask you what is another name for a to the power of minus 1 to the power of 5, we just learned that this is by definition the same thing as a to power minus 5. So something like this. Usually you can convince yourself that what we learned for positive powers is also working for negative powers. Yes? Okay, there are 2 more examples that I want you to do to convince yourself that this is correct. By the way, let me just switch back here and then go here. So for example, this example, could you expect that this is true? I have written, you see, I haven't asked you to prove it. I want you to feel that you can do these things quickly, yes? Then, for example, one can write a to power 4 times a to power minus 6. You don't need to justify. You just simply write a to power minus 2. And if I ask you what is a to power minus 2 times a to power 2, it becomes a to power 0, and a to power 0 was defined to be the identity matrix. And if I have a to power minus 3 to the power of minus 2, I can write a to power positive 6. Okay? But which rule of powers was not applicable in matrix theory? Do you remember? So these differences you should remember in this course, yes?
Maybe powers that aren't all numbers.
No, that was, so let me just switch back to here. It was like this. Do you remember I told you that this formula that a, oh, this is not a good color. So a times b to power 2 is not necessarily equal to a to power 2, b to power 2. This is not in general true, yes? But if a and b are numbers, this is definitely true. So this is the rule, which was an exception, because matrix multiplication does not have commutativity in general. So in general, this formula, which was true for numbers, it is not true for matrices. So this remember. But as far as you are not using this rule, you are on the safe side actually. Okay, so I just want to wait for you a little bit to simplify these expressions as much as possible, and that would be the last example for today, and this discussion is finished. The idea of the inverse of the matrix is not finished yet. Why? Yes, why the inverse, why the topic of the inverse of a matrix is not finished yet? There is one main reason. Might be you can cook up a lot of reasons, but there is one main reason. Yes.
Because we haven't gone through fraction powers.
No, fraction powers will not study. Okay, but no, that is the inverse of a matrix. The topic of the inverse of the matrix, in principle, you should feel it. It is not finalized. Why is that? There is a very natural reason that this shouldn't be finalized at this moment. Because we didn't answer one question, which was a very important question. What was that? We didn't learn how to obtain, how to derive the inverse of an invertible matrix. Yes, I told you a lot of theories. Yes, I work with letters abstractly, but assume that I give you a matrix, a square matrix with numbers in it, and then I ask you what is the inverse of this matrix. So first of all, how can I realize that the matrix I give you is really invertible? You remember the topic? Even if there are no zeros in the matrix, there is still no guarantee that this matrix is invertible. If you go back to the first part of this lesson, I gave you a 2 by 2 matrix with no zero entries in the matrix, and then I proved for you that this matrix is not invertible. Okay? And so this is a very important question we haven't addressed yet. And that is the motivation of the next lesson, which is called the determinant. So we want to use determinant means something that determines something. And that determines if the matrix given to you is invertible or not. So that would be the next chapter. So I want to start that. So the two questions are left. I give you a matrix, really matrix. You can feel it. You can see numbers in it. Yes? A block of numbers, a square block of numbers. And then I ask you, is this matrix invertible? How can I understand that systematically or simpler? And then if the answer is yes, how can I determine that inverse? So these two important questions are still left unanswered. We have to come back at some point and answer them, and hopefully we have enough time to cover that topic as well. Okay? Okay, now I go back to these slides and I want you to actually try to simplify these things. So the goal of this exercise is just to practice a little bit about the formulas. That's it. Just do it for me, please. Thank you. Okay, so I think it's very simple, yes? So what is the answer to the first one? It's just like numbers, except that you have to be careful you're not allowed to use commutativity. Yes, but more or less all the rules are the same. So what do you do here for the first one? If you want to write it a little bit explicitly, so you just keep the first one, but do you remember the rule?
You switch the places.
Yeah, we have to switch the places, so this becomes a to the power of 4 to the power of minus 1, and then b to the power of 3 inverse. By the way, we kind of, okay. And then b to the power of 4. But we just learned that what can I do? I can write a to the power of 4. A to power 4 to an inverse is just a to power minus 4. And the other one is b to power minus 3. And then I have b to power 4. But what can I write for this part? I. So just ignore that. It is I. And then what can I write here?
B.
It's just b. So the simple answer to this one is b. So we were able to simplify that. So you see that I'm not using commutativity. Okay, so the second one is more or less the same thing. So it becomes a to power 3, b to power minus 6. And the middle one is, okay, we can do it quickly, yes? b minus 6 inverse, which is b to the 6, and a to the power of minus 2, and then a to power 4. But the middle one is, this one is just simply I, and then it becomes a3, a to power minus 2. So let me just write all of them once. So this becomes a to power 3, a to power minus 2, a to power 4, which is what? A to power 5. Yes, so that's the answer to this one. Yes, and then the next one is also very simple. So this is just b inverse. Then I have b to power. And so, by the way, how should I interpret this, by the way?
B to power 2.
So, in principle, let me tell you here, that's a little, let me just try to convince you here. If I ask you to do this, what do you do, yes?
I wrote ab to the minus 1, and the whole thing to the minus 1 to the positive.
Exactly. So that's the way you do it. But then you will learn that you can also, so you can do it like this: b minus 1 to the power of minus 2, a to the power of minus 2. So you can do this quickly. But again, as Aaron mentioned, this is the reason we can do that, because this one means ab inverse to power minus 1 to power 2, as just we learned. And then for this inverse, we know the rule. What is the rule? Is to inverse in the reversed order. So the inverse of b inverse becomes b, and the inverse of the first one is a inverse. And then I have a power of 2. Okay, by the way, so you see that this is wrong now. Yes? So this means b times a inverse times b times a inverse. So the one that I wrote is completely wrong. So that is, by the way, it's important. So even if you are experienced, you might make some mistakes. So you have to really go through the definition to see if everything works fine. So we cannot continue more than that. So for this middle one, I can write this. I can then write it like this, and then I repeat it 2 times. Yes? So, but remember, I take this with me and put it here, and after that, I have my a here. So that's what I want to do now. So I go here, I put b, a inverse, b, a inverse, a. Yes.
You already wrote the first b.
Pardon?
You don't need to.
I don't need to. Okay. I wrote 2 b's, yes? Oh, sorry. Yes, you're right. So let me write it more organized now. So you see, this b inverse is the one that I put here. Instead of the middle one, I put this. So what happens? It becomes b a inverse, b a inverse. But after this is finished, I have an extra a. I put it there. Now you see that this part is I. This part is also I. So what is left for me? A inverse b, which I cannot simplify any further, so I have to live with it. So that's the answer to this part. So be careful. So you see, even though there are less matrices involved, this example is harder than the previous examples because you have to have a good interpretation of what does it mean. Okay? And the interpretation that I first wanted to try to sell you was completely nonsense. That's wrong. Yes? This is correct if, of course, A and B are invertible, which we don't, are commutable, which we don't know yet. Okay, any questions? Okay, so we stop here. Thank you.